Good afternoon, colleagues. We bring to your attention a report on the topic, Data Structures and Route Reduction Procedures in the Problem of Distribution and Routing of Flows in a Communication Network. Introduction. In the problems of optimizing the distribution and routing of flows in communication networks, the input data is vehicle routes or data transmission channels, see in 1. In terms of graph theory, a route is a simple path given by the enumeration of nodes and arcs of a network. Circular routes in which the initial and final nodes coincide are allowed. A set of routes can be initially specified or generated according to certain rules in the process of solving a problem. Because routes have different lengths in terms of the number of nodes, or arcs, included in them, shorter routes can coincide with longer routes, both in nodes and in arcs. For the distribution of flows in such problems, special data structures are used, abstract data types, ADT, see in 2, 3, with the help of which the relationship between distributed flows and routes is described. Route reduction procedures can significantly reduce the number of such connections in the case when the number of initial or generated routes in combinatorial optimization problems is very large. The article discusses data structures and procedures for route reduction, which are used in algorithms for solving the problem of optimization of distribution and routing of flows. The developed algorithms for route reduction allow solving the problem of distributing flows when the number of specified routes is too many, and the amount of RAM of the computer is limited. Estimates of the complexity of algorithms for reducing routes by nodes and arcs, as well as the algorithm for forming a reference data structure, are obtained. The proposed algorithms were tested on networks with the number of nodes from 50 to 500 and the number of routes from 1225 to 124,750, which showed their operability, good computational efficiency, and they can be used in practical problems of distribution and routing of flows on large-dimensional networks. Data structures and route reduction procedures. Let G, NP, a multi-commodity network with a set of indirect topological arcs P equals P, a set of nodes N equals N. A topological arc is a physical segment of a communication line. Network nodes correspond to the points of departure, receipt, and transshipment, switching, of flows. A matrix of flows is defined on the network U equals Uij. Flows Uij from sources I into the drains J, must be transported in vehicles or transmitted through communication channels. A set of vehicle routes or communication channels is also specified Mk, each of which consists of a sequence of nodes and topological arcs of the network G, connecting the start and end nodes of a route or communication channel. In a particular optimization problem, the set of routes may not be specified, but searched. For data networks, routes can be represented by simple communication channels connecting adjacent nodes or switched communication channels connecting any sequence of nodes, dedicated channels. In the individual case, all specified routes can coincide with the topological arcs of the network. Plural Mk can contain multiple routes, nodes connecting any pair. An additional route multi-network is defined Gm, N, Pm, where N, a set of network nodes, Pm the set of its oriented route arcs. Between any nodes I and J network Gm there is a route arc if they are connected by at least one vehicle route or communication channel with Mk. As you know, the computational efficiency of algorithms largely depends on the successful representation of the data structures used in the process of solving the problem. When solving the problem of distribution and routing of flows, it is necessary to have such a data structure that, on the one hand, would allow for each flow which quickly find the set of routes to which this flow can be allocated, as well as define the set of flows that can be implemented on this route. On the other hand, the data structure should ensure the storage of the results of solving the problem, a flow distribution scheme in which for each Uij defined path from the original I node to the end J node with directions and transit nodes. Another important requirement for the organization of the data structure is the minimum of information stored in the process of solving the problem. Let's define the reference structure HS, consisting of a matrix of pointers delta ij and elements e, linked in unidirectional linear lists. Index delta ij corresponds to the flow uij and points to the first element e, which is called the head of the list. Every element e may have a link to the next item. The last item in the list has a null reference, null, link, and is called caudal. Every element e consists of a field fwd, that keeps the reference on the next element or value null, field amRoot, indicating the address to which this flow can be distributed, and feature fields dm. Fig 1 shows an example of a structure HS which explains the concepts introduced. From the rules of initial formation HS, it is clear that the number of elements E in the lists HS depends on the number of roots and is defined as follows. In this regard, let's consider the reduction procedures that allow you to reduce the dimension of the structure HS. Let the root M alpha reduce to a root M beta by nodes, if the condition is met, and is reduced along topological arcs if obviously, root reduction reduces the number of connections in the network GM and the number of elements in the structure HS by the amount, where k*, the set of numbers of reduced roots. After executing the reduction algorithm, a reference structure is built. At the same time, only such roots are visible, in which VRI equals 0. Obviously, after executing the reduction algorithm, the amount of RAM of the computer occupied by the reference structure HS will be reduced by the amount of, where VE is the amount of memory occupied by one item in the list. The time complexity of reduction algorithm by nodes is on average. And in arcs, operations, where, average root length. Root reduction is extremely necessary if the initial set of roots is all possible roots. In this case, the dimensionality of the problem increases sharply, taking on the character of building new, previously non-existent roots. Algorithm for the formation of a reference structure HS with the simultaneous construction of root arcs of the network GM is also given in 4. Medium complexity of the algorithm for the formation of the reference structure is operations, where the number of reduced roots, and average root length. For the initial distribution of flows on the network GM, an algorithm is used to build the shortest paths according to the criterion, minimum transit overloads. If the number of overloads is equal, the minimum length of the path. See in 5. Conclusion. The paper develops data structures and algorithms for root reduction, which allow solving the problem of distribution and routing of flows in the case when the number of specified roots is too many, and the amount of RAM of the computer is limited. Data structures based on linear dynamic lists are proposed, with the help of which you can quickly find all possible routes for distributing flows in the network. The proposed algorithms were tested on networks with the number of nodes from 50 to 500 and the number of routes from 1225 to 124,750, which showed their efficiency and good computational efficiency, and they can be used in practical problems of distribution and routing of flows on large dimensional networks. On the basis of the proposed data structures and heuristic approaches, polynomial algorithms and a computer program have been developed. C6, for solving the NP-hard problem of distribution and routing of flows of transport block. C7. Estimates of the time complexity of algorithms are obtained. Thanks for your attention.